Welcome back. In the last part, we explored the structure of inheritance and how we build class hierarchies using base and derived classes. Now, we take it one level deeper into runtime behavior and how the C# runtime handles method calls when polymorphism is in play. We'll also explore how to override base class behavior responsibly, how the root object class influences all types, and how constructors behave in inheritance chains. Dynamic binding means that the decision of which method to run happens at runtime based on the actual object type, not the variable type. For this to work, the base method must be virtual. The derived method must be override. This lets us write flexible, generic code that still respects specific behaviors at runtime. It's how polymorphism becomes real, late binding in action. C# provides two distinct ways to modify method behavior in derived classes, overriding and shadowing. When you use overriding, which requires the base method to be marked as virtual and the derived method as override, you effectively replace the original method. This ensures that polymorphic behavior functions correctly, allowing derived classes to exhibit their own implementations. On the other hand, shadowing involves using the new keyword. This approach hides the base method instead of replacing it, meaning that polymorphism does not apply here. Choose overriding when you want to maintain polymorphic behavior across your classes. Reserve shadowing for situations where you intentionally want to break that behavior, though this is typically a rare and risky decision. Example: scholarship student overriding credits. Here we override the credits property of student. In the base class, credits multiplies by a rate to calculate tuition. In the derived class, scholarship student, tuition is always 0. This shows real-world polymorphism, same interface, different behavior. The student still has credits, but the meaning of that value is different. In this example, we create both a regular student and a scholarship student. We assign the same number of credits. We print tuition. The result? One pays full tuition, the other pays 0. Same property, different behavior. This is dynamic binding, working with polymorphic types. Code stays clean. Behavior stays accurate. When a derived class needs to extend a base method, not replace it, we use the base keyword. Example: commission employee wants to reuse getGreeting from employee. Then append custom text, I work on commission, and this lets you reuse logic safely while still customizing the output. Think of base as a bridge, not a replacement. Shadowing example: new greeting method. The new keyword defines a new method in the child class with the same name as the base method. But remember, this is not overriding. If you reference the object through a base class variable, it calls the base method. This is shadowing, and while legal, it often leads to confusion and bugs if misused. Stick to override unless you have a strong reason not to. Summary of polymorphism tools. Quick recap of behavior control and inheritance: virtual plus override, true polymorphism. New, hides base method, breaks polymorphism. Base, explicit call to the base class logic. These are the control switches that let you fine-tune inheritance safely. Use them intentionally, not accidentally. When you assign a derived class object to a base class variable, C# does it automatically. This is called an implicit reference conversion. Example: car my car equal new car. Vehicle my vehicle equal my car. This works because of the is-a relationship. Every car is a vehicle. It's part of what enables polymorphism in the first place. This is called implicit reference conversion. It works because every car is a vehicle. This mechanism is crucial to polymorphism. It lets you store different objects in the same collection or pass them through generic code. Every class in C# ultimately inherits from the object class, even if you don't write it explicitly. Object, lowercase, is just an alias for system object. That means every class has default implementations of toString, equals, get hashcode, getType. These are the universal tools available to all objects. Understanding this root relationship helps explain why all types have certain capabilities by default, even if you don't declare them. For instance, getType, a method from the object class that returns the actual runtime type of an object. This is especially helpful in polymorphic scenarios, where you may be using a base reference but want to identify the true class underneath. By default, toString returns the class name, not very helpful. When you override it, you give meaningful, human-readable output. Example, public override string. toString will print class employee, ID num, name. Now every time you print that object, it tells a story, not just a type name. By default, equals compares memory references. But often we want to compare content. For example, two employee objects with the same idnum. Overriding equals gives value-based equality. Key rules: check for null, ensure same type, compare key fields, ensure symmetry and transitivity. This makes your objects behave more like real values, not just memory blobs. When you override equals, you must also override getHashcode. Why? Because many data structures, like dictionaries or hash sets, rely on the hash code. If two objects are considered equal, they must return the same hash. This is part of object contract consistency, fundamental to safe behavior in collections. getHashcode, used in hash-based collections like dictionaries and hash sets, must return the same hash for objects considered equal. If you override equals, you must also override getHashcode. Otherwise, data structures may misbehave. This is about keeping the contract between equality and hashing consistent. Summary: object class methods: getType, runtime type info, toString, human readable string, equals, logical equality, getHashcode, integrity in hash-based collections. These methods are foundational. Understanding and overriding them gives your classes professional behavior out of the box. When a derived class is instantiated, the process begins with the system object constructor, which always runs first. Next, the base class constructor executes, followed by the derived class constructor. This top-down approach ensures that the general class logic is established before any specific setup occurs. Understanding this order is crucial for safe object construction, as it lays a solid foundation for your derived classes. Thank you for tuning in. Default constructor with base. Example shows how a derived class like student can call its base class constructor using semicolon base. Even though the person constructor is default, explicitly calling it with base keeps your intent clear and code maintainable. It demonstrates constructor chaining, critical when the base class does something important during initialization. Here, the derived class student receives several parameters, some of which are forwarded to person. This maintains encapsulation and leverages initialization logic already written in the base class. Again, this is good OOP design, reused through inheritance, not repetition. Well done. You've just completed one of the most advanced and powerful topics in object-oriented programming. Let's reflect on what you now know. You understand how polymorphism works at runtime via virtual methods and dynamic binding. You can now override, shadow, or extend base behaviors as needed. You know how the object class gives every type in C# a shared set of behaviors, and when to override them. You've seen how constructor chaining ensures predictable object initialization across inheritance trees. These skills are the core of designing flexible, robust, and professional-grade software.